Today our topic of discussion is plasma oscillation and plasma frequency. So what do you mean by plasma oscillation? Suppose we have a system of plasma. Suppose it contains plasma, and plasma consists of positive ions and negatively charged electrons. And they are distributed in the plasma such that overall plasma is neutral. The overall charge of the plasma is neutral. That means they maintain a neutrality throughout this plasma. Okay. So now you see, when these electrons are displaced, an electric field is generated in the direction such that they are pulled back to their original position. Let me show you how. We know that in a plasma, these positive and negative ions, negative charged particles are free to move. These are the suppose positive ions, and these are negative electrons. Suppose black dots are negative electrons, and in red color they are positive ions. Okay. When they are displaced from their position in this direction, then what will happen? An electric field will generated, and these positive ions will pull these electrons to their own position, and due to inertia they will swing through them, the positive charge due to inertia. Then again they will pull back to their original position, and this phenomena continues, and that's how oscillations occurs. Okay. Now let me show you how. And the frequency of this oscillation of electrons is called plasma frequency. Now you see, not only the electrons are oscillating, also the ions are also oscillating, but here you see, as ions are more massive than the electrons, so most of the oscillation is performed by electrons. We can consider like this, because you see, suppose this is an ion and this is an electron, suppose, and let me represent the displacement of this ion by this blue line. This is the suppose displacement. Let me displacement of this ion. Then at the same time displacement of electron, let me represent that by the red lines. Okay. So comparatively we can consider this these ions are steady. Okay. So now let me show you how to derive the plasma frequency. In order to derive plasma frequency, we need three equations. One is equation of motion of fluid in terms of electrons, or you can say momentum equation. Then equation of continuity, then Poisson's equation. So we need these three equations. Now let me show you. So let me write the plasma frequency, the equation of motion for the electrons in a plasma fluid is given by m Ne within bracket del T of VE plus VE dot del into VE is equal to minus E NE dot capital E into capital E. This is equation number 1. So these are vector quantities, remember that. Okay, now you see, actually we have got the momentum equation in this form on the right hand side, Q N E plus V cross B, isn't it, in this form. But here we are not applying the magnetic field, that's why this term is missing, and the charge of electron is given by minus E here, so that's why we have got this equation. So I hope you have got it. So now equation of continuity, that is del N by del T, del Ne by del T plus del dot Ne VE is equal to 0. This is equation number 2, suppose, and the Poisson's equation, that is epsilon naught del dot E, that is divergence of E, is equal to minus, sorry not minus, E into Ni minus Ne, and this gives the surge density of the plasma. Okay, now here you see, so let me give it is equation number 3. So what is here Ne? Now let me tell you, Ne, we will write Ne is equal to N naught plus N1. Okay, where N naught is the number density, of particles at equilibrium position when the plasma was steady at equilibrium. N1 is the number density, change in number density after oscillation takes place, change in number density of the particles. Now the overall density, overall change is given by Ne, that is number density of electrons after oscillation starts, is equal to N naught plus N1. Similarly, we can write for VE, we can write V naught plus V1, and for E is equal to, we can write E naught plus E1. Now at equilibrium, here you see, we can say at equilibrium this N naught, it is the number density of particles at equilibrium state, is equal to Ni, that will be number density of the ions as well. Okay, so at equilibrium there is no change in particles density, that's why N naught must be equal to Ni. Now if you use this here, so before we use this here, let me tell you something again. And at equilibrium, as the change in number density is 0, therefore gradient of N naught must be equal to 0, and also V naught and E naught must be equal to 0. Here you see V naught. So before oscillation takes place, V naught was equal to 0, and if there is no oscillation, there is no electric field generated, so E naught is also equal to 0. So hope you have understood this topic. Now here you see, therefore obviously del N naught by del T is equal to del V naught by del T is equal to del E naught by del T, must be equal to 0. Now these conditions, we will use these conditions in those equations 1, 2 and 3, okay, to apply the linearization method. So let me write those things on the right hand side. Okay, so let me write here. Okay, now you see the equation number 1. From equation number 1, what we get? So replace this NE by N naught plus N1, VE by V naught plus V1, and E by E naught plus E1. Then what we will get? So let me write here. So then we're going to have M into N naught plus N1 within bracket del del T V naught plus V1 plus V naught plus V1, then dot del into again V naught plus V1 is equal to minus E N naught plus N1, then E naught plus E1. So from equation number 1 we have got this. So now you see, in this case, this E naught here in this case, let me write here you see, from the both side you can cancel these terms. Then as I have already told you that V naught and E naught, these are equal to 0. So this terms gonna be equal to 0, this terms gonna be equal to 0, V naught only here 0, okay, then E naught is also 0. If these are 0, then what we will get? This equation is going to be reduced to, let me scroll down. This equation number is going to be reduced in this form: M del V1 by del T plus V1 dot del into V1, okay, in bracket, then minus E1 here. As you can see, this term is second order term. So if we apply linearization, then this second order term will become 0. This should not be included. So that's why this equation is reduced to now M del V1 by del T is equal to minus E1, capital E1. This is equation number suppose 5. Now similarly, from equation number 2, if you put NE is equal to this, NE is equal to N naught plus N1, then VE is equal to V naught plus V1. So then what you will get? Now from equation number 2, so from this equation, the second equation, we will get del T of N naught plus N1. So this NE is replaced by N naught plus N1, then plus del dot NE is replaced by N naught plus N1, then VE is replaced by V naught plus V1 is equal to 0. So let me scroll down. Okay, now here you see, in this case at equilibrium V naught is 0, so let me use this, V naught is 0. Okay, so now this equation is reduced to, now let me show this term only. So from this part we got del n naught V1 plus n1 V1. So here if you linearize, so this term will be 0, and from here you will get, so this thing can be written, this thing is equals to n naught del dot V1 plus V1 dot del n naught. So this terms is equal to 0. So here we have already got del n naught is equal to 0. So, and from here you see derivative of n naught with respect to time, that is also 0. Here we have got this equation, this relation. Okay, so from this relation we have got this thing is 0. So we will get, so that means this equation is now reduced to del n1 by del t plus n naught del dot V1 is equal to 0, and this is suppose equation number 6. This is equation number 6. So from this third equation, from this Poisson's equation, if you replace this Ne by n naught plus n1, here you can see, then what you will get? Then equation number 3 becomes epsilon naught del dot E is equal to, so what was the equation? Okay, this is, so from here we will get E Ni minus n naught minus 1, sorry, not 1, n1, not only 1, n1, that's going to be n1. So now you see at equilibrium Ni is equal to n naught. So I have already mentioned this thing, so these two will be cancelled. So as a result we will get, so this is equal to minus E n1. This is suppose equation number 7. This is equation number 7. Now if oscillating quantities are assumed to be sinusoidal, so we have discussed this in plasma wave also. So now assume that oscillating quantities are assumed to be sinusoidal, then we can write here that n naught, sorry, not n naught, n1 is equal to n1, let me write here bar to represent the amplitude, e to the power I kx minus omega t, where omega represents the plasma frequency. So then V1 bar omega t. Similarly, so if the direction of oscillation we can consider the x direction, then x cap should be there, then E1 will be equal to E1 bar e to the power I kx minus omega t. So here also we have to write x cap. So now if we differentiate any one of these equations, with respect to time and with respect to x separately. So let me differentiate n1 is equal to n1 bar e to the power I k x omega t. Let us differentiate this equation, differentiating with respect to time, suppose. Okay, so let me give you this equation number 8. So we can write differentiating equation number 8 with respect to time, then what we will get? Del n1 by del t is equal to, if you differentiate the right hand side, then what will get? You know how to perform the differentiation. So then we will get n1 bar del t of e to the power exponential e to the power I kx minus omega t. If you differentiate it, then what you will get? Minus I omega t, not t, it should not be t, n1 bar, then e to the power I kx minus omega t. Now you see this term can be replaced by n1 again from equation number 8. So then we will get minus I omega n1. Okay, so from equation number 8. So now if you compare this right hand side and left hand side, so if you compare these two, then you can see we can compare del t with minus I omega. Okay, if you compare, then you can see you can write del t as minus I omega. So we can replace. So let me differentiate again before that, before writing that. Let me differentiate. Differentiating equation number 8 with respect to x again, and if you differentiate with respect to x, then you will get del n1 by del x is equal to n1 bar del x of e to the power I kx minus omega t. That's going to be equal to minus, here not minus, ik n1 bar e to the power I kx minus omega t. Now again you see this part, this portion n1 bar e to the power I kx minus omega t, this can be replaced by again n1, this value. So doing so, we will get minus, not minus, ik not t, this one we will get n1 again. Okay, n1. So here from this equation, comparing here left hand and right hand side, we have got that we can replace del t by minus I omega, and from here if you compare the left hand and right hand side, then you can see here, let me scroll down, del x can be replaced by ik, and in 3D you can replace the del operator by ik. Okay, so hope you have understood up to this. So let me write in the above equations, in equation, so in those equations that we have got here, equation number 5 and equation number 6 and equation number 7. Here we will replace del del t and del del this del operator by this we have got here minus I omega and ik. Then what will happen from equation number 5? In equation of 5, 6 and 7, replacing del del t by minus I omega del by ik, then what we will get? We get these three equations are minus I m omega v1 minus e small e and capital E1. Then we have got this one from 5, okay, and from 6 we have got minus I omega n1 is equal to n naught ik v1, and 7, from 7 we will get ik epsilon naught E1 is equal to minus E n1. Okay. Now here you see this equation can be replaced by not this one. So from these two equations, so what we can do? So here you see from this equation, from this one we can find n1. n1 is equal to here. So here you can see this I cancel. Then n1 will be equal to minus, here minus minus also cancel, you can see. So n naught k v1 by, you will get omega, you will get this thing, isn't it, omega. Now if you use this value of n1 in this equation, then what will happen? Then it implies ik epsilon naught E1 is equal to minus E n naught k v1 by omega, you will get this one. So here you see this k cancels down. Okay. So now what we will get from here, we can write that E1 is equal to, this equation implies E1 is equal to minus E n naught v1 by I epsilon naught. These two terms are brought here and omega also there. Okay. So if you multiply both the numerator and denominator by I, then what we will get? We will get I E n naught v1 by epsilon naught omega. Now let us use this value of E1, this value of E1 here. Let me replace this E1 by this value of E1. Then what will happen? Then doing so, that means we are solving these three equations. Okay, that's it, nothing else. Okay, then we will get so let me give it equation number suppose 9, and this is suppose 10, equation number 10. Now use 10, using 10 in 9, then what will happen? We will get minus I m omega v1 is equal to minus E, and instead of E1 we will put I E, and we will put this value E n naught v1 by epsilon omega. So here you see what we can cancel in this v1, this v1 cancel here. Then again you will get here anything else. Okay, you can cancel I and I. Then what you can cancel here? Nothing, I think. Yes, nothing can be cancelled, and one more thing, minus minus will be cancelled. Okay, then so this omega will be multiplied with this one, then you will get omega square, then this m will be multiplied with epsilon, not here, then you will get then e and e, that is e square n naught by epsilon naught m, or m and epsilon naught. So this implies omega is equal to n naught e square by m epsilon naught whole to the power half, that means square root. So this is the expression for plasma frequency. Okay, this is the expression for plasma frequency. So hope you have understood. So if you think it is helpful for you, please share the videos with your friends, and so thank you for watching.